To get everybody's attention, we have today with us Dr. Raymond Brown. Dr. Brown, he's got a really distinguished history. Before coming to Houston, he was the chair of the physics program at Clark Atlanta University. And now he's teaching at University of Houston downtown. And what he's going to be presenting today is talking about using Mathematica in the introductory physics courses. And so he's actually kind of stepping into some physics education research.
Thank you, David. Thank you all for being here. Is everyone a UHCL faculty member? Is that who I'm addressing? Students or anyone from any of the local community colleges? I want to talk about using computer algebra systems to address some physics education problems. I spent about 20 years in private industry, and before going back to academia. It seems that people who work in technical professions in public or in private industry, if they have contact with academia again, they sort of have this mission because they've encountered, freshly minted graduates with bachelor's degrees in engineering and sciences, chemistry and physics, even from prestigious universities where we expect that they would really be competent coming out of that. And find that they really don't have what the curriculum for the universities said they should have. This tends to irritate people in private industry because it's expensive. They've got to spend money training them or spend money, hiring to start with is expensive. And even firing people is expensive. So we certainly don't like having to teach them things that we think the college should. Anyway, you get back into academia and you say, I'd like to ensure that these graduates know their stuff when they finish. In the course of time, I ran across Mathematica and immediately started using it myself. And it seemed to me to be a tremendous tool to help with teaching physics in particular, or mathematics or any sciences. But UHD is the first place where I've actually had the institutional support of a site license for the product, or any CAS product for that matter, any computer algebra system. So upon discovering that, and the fact that it could be freely available to all faculty members and all students, then I started talking with the colleagues there about, how can we take advantage of this? And I've had years to think about how I would take advantage of that kind of situation. And some of those ideas, we've developed a program to put in place some of that. We started with, in January, with the spring semester, teaching while using Mathematica fairly intensively in the laboratory course. This is the courses that we teach at UHD are algebra and trig-based physics. We're not offering any calculus-based physics, and there's none of the typical courses that you'd find in the upper-level physics curriculum. No advanced mechanics, no electrodynamics, no quantum mechanics, statistical methods. Those are mathematical methods in physics, thermodynamics. We're basically a service group within the natural sciences department. The academic role that we most heavily play is teaching these algebra and trig-based introductory courses. The students are primarily biology, chemistry majors, engineering technology majors, There's not a physics degree at the school, so there's no actual physics students. On the other hand, this is a little of the background that I was talking around. The chair of the department there and the other physics instructors were interested, intrigued almost, with the idea of using this and the fact that, or the idea that it might enhance learning of physics with the students. And we had a few conversations about how we might implement this, or how we might first start thinking about implementation. And the consensus was that we would rewrite the laboratory course. We had some other changes that we wanted to make in the physics one, that is the mechanics laboratory course. And so those were, the lab manual for that course was rewritten. And we've implemented the use of the computer algebra system software within the courses. And the beginnings of that program and what we're trying to do with it is what I'll talk about tonight, with a little bit about the kind of results we're seeing to this point. Other changes we were making at the same time in the laboratory class. This was the most important change, we thought. Institute a consistent emphasis on determinations of experimental uncertainty. To address that, and we decided we wanted to go into greater depth with a smaller number of laboratory experiments. So the number of experiments was reduced from 10 to 6, and the process is that we spend 2 weeks on each of the experiments. Basically, both weeks can be the entire experiment, but the students are take data and generate their lab report within a period of about 3 days. We've got to get that back and have time to grade it and return it for the next laboratory meeting. So they see the marked up first draft reports and have the opportunity to rewrite to a final draft. Yeah, that's a model that some of the biology lab courses at UHD had already implemented. They were pretty pleased with. So the chair was being a biologist himself, and one of the implementers of that kind of story for the biology classes was happy enough for us to do it in physics. What were our goals in attempting to do this? These are pretty much the educational goals one has for these kind of courses, any introductory physics courses, really. I've listed 4 of them here. An emphasis on symbolic solutions to problems, avoiding calculation errors and evaluating complex expressions. And this is not much, these are not really educational problems in the upper levels, because the students who reach the upper level courses have mounted, scale these little mountains. And then we also, because of the kind of careers that the students that we're serving are likely to go into, giving them, allowing them, and showing them a way of gaining some familiarity with computer-aided systems or software, would be of benefit, because, well, let's go through these in a little more detail. This first one is the one that I find I spend most of the time with students trying to get over, is the importance of basic symbols, assigning physical quantities symbols that one can use in the equations, in relationships. That sounds like a simple thing, but the students that come to us, by the way, this is an open admissions university, so we'll have students who come in, and the only requirement for them being admitted into starting our course basically is to have had high school courses in algebra and trig and have a high school diploma. So they frequently come with very poor mathematical backgrounds and some very bad habits. In particular, the impulse, it's a trained impulse actually, to immediately convert any problem they encounter into arithmetic problem, and to avoid anything higher than arithmetic if they could possibly can. So in order to succeed even with an algebra and trig-based introductory course, they've got to address the mathematics at a higher level than that. And so it's basically having to unlearn an old habit in order to move on to more demanding work. Avoiding calculation errors and evaluating complex expressions. Say more. See that open just a minute. Even in the laboratory, they will encounter, at least in some of the experiments, the need to evaluate solutions. The primary example that I'll use and address a little later is the calculations of the range of a projectile, solving the kinematic equations in a general solution, a general situation. They find that solution to be complex and difficult to work through, and in my experience with even calculus-based courses, students taking calculus-based courses, that using a handheld calculator, roughly 10% of the students would succeed in calculation like that. Whereas, and they would spend quite a bit of time agonizing over the arithmetic. Consider that time wasted. They're not learning about the concepts, learning about the relationships while they're struggling with arithmetic. Gaining familiarity with CAS software. Students who are awarded degrees can expect in their work careers to become competent and do use of some sort of technical software of some sort. And CAS software is the epitome of that type, and even including things like financial and workflow software. So we're presuming in this goal that any familiarity they gain with this product that we're using, with Mathematica, that will pay dividends. And finally, gaining an understanding of using software of this type to actually generate symbolic solutions to problems. This is closely related to the first two goals. And, well, the problems that our students struggle with, the problems in the textbook. Okay, so this is a freshman level textbook, and the problems are simplified to make them handleable at that level. Okay? And they struggle quite a bit with that. It's convenient for an instructor to say, well, you know, it's a prerequisite for this course that you be familiar with algebra and trigonometry. And many of them can say, oh, but I am, you know, and they can point to a high school transcript where they got A's in those courses. And I do some algebra at board and just get blank stares. Because I question that, you know, replies like, I've never seen that done before. So we can't insist that they already have a full understanding of the algebra. What I'd like them to get here is an understanding that where they are struggling with some of those solutions, that the CAS software can at least point them and show them the kind of solutions that a machine can generate. And then if they can understand those, they can understand how they got to them as well. But this is something that's we're really not addressing very effectively in the laboratory course. Don't have a lot of traction on that goal. The methods that we're using. There was a minimum amount of actual physical changes to the laboratory to implement this, starting from our series of the traditional mathematical curriculum, where each week they do an experiment, they take some data, they do some analysis, they turn in some sort of report. We basically made no change in those traditional experiments, but we reduced the number and added an analytical insistence really on including in their analysis an actual consideration of the experimental uncertainties calculated from their data. So our students never more see anything like calculating a percent error, a laboratory result from some standard value. They're calculating uncertainties from their data, determining agreement with a standard value or any theoretical hypothesis from the evidence of the data, using certainties from those data. So that's a considerable increase in the depth of the analysis. We did reduce the number of experiments from 10 to 6 because we, honestly, thought that was going to take us as instructors probably 2 weeks to have a reasonable chance of success in grading that increased analytic depth to the students. Written materials, these were changed pretty significantly. First of all, all the written materials are on the course management system software for the course. So they're no longer buying a lab manual from print shop. The lab manual is basically a list of 6 files, one for each of the experiment formed in the semester. For each of those 6 experiments, the lab manual is presented. It can be downloaded in 2 forms, 2 formats. There's one in Mathematica format, which is actually used to do calculations with the data during the laboratory periods, class meetings. There's also an Adobe Acrobat file that's just a copy of so that many of the students do not have the Mathematica on their own computer. Many of our students don't have their own computers, period, and depend upon the computer laboratories on campus. But these files can always be read no matter if they've got a computer that can connect to the internet and get to the class website, then they can read these files. It has really all of the information. By the way, we're not making the use of the software mandatory in any way. It's entirely optional. There's no grading. We're not really teaching them how to use the software except with guided examples. I mean, there's some presentation within the lab manual for each experiment of how they can use the software, but it's not required. And many of the experiments they could do without the software quite as well as with it. There's a laboratory report template. Now, what we do with the template is basically all of our requirements for a lab report. What the sections are of the lab report, what their names are, what's the material that goes in each section. So that's much like a template any private company have for their technical reports. The template is also, they can use it directly, simply edit the template with the content of their own lab reports. And this is typically what's done. We'll take one of the templates, replace the instructions with their own text, and turn that in. I'm teaching 3 of those laboratory sections. There's a total of 5, and 2 other instructors, one a full-time faculty member, the other an adjunct. One each. They each have one of the other 2 lab sections. Those instructors are requiring the reports to be printed and turned in on paper. I gave them the choice of either printing them or submitting them as electronic files. I originally, in the fall semester, was giving people that choice because I definitely preferred to get the electronic files. That semester started with about a 50-50 split between printed reports and electronic ones. By the time it was 2/3 through the semester, it was 100% electronic. This semester, it has been 100%, well, with the exception, I think, of 2 reports that I've gotten from students that were printed. The rest have been electronic. The students prefer the electronic format, as I do, I think. They can choose to use the templates either in Microsoft Office Word 2007 format, Mathematica format, or they can simply download and read it in Acrobat format. Of course, they can't edit that, so the only purpose the Acrobat format has is for them to read the template and know the requirements for the lab report. But for the Mathematica and the Microsoft Word, they can actually edit the template and turn it into their lab reports. I found that to be, the students take to it very willingly, and I find it much more pleasant duty. If it's possible to talk about grading lab reports, it's pleasant duty. It's more pleasant when they're electronic files than if they're paper. I gradually, over the years, become very averse to hauling papers around. Another file that's part of the materials is an appendix on experimental uncertainties, where we provide instruction on the meaning, the use, and the determination of experimental uncertainties. We describe these in the short lecture before each laboratory experiment as well, those that pertain to the experiment that's going on. So there are statistical methods, there are shortcut methods that can be applied in most experimental situations, appropriate for the determination of uncertainties, both in the directly measured data and in quantities calculated from the data. The statistical methods for dealing with uncertainties, it's a very broad topic in general, and technically can get very detailed. None of that sophistication is needed for the introductory physics laboratory. So we basically simplified the statistical methods and aimed them directly at the applications that they can encounter in the laboratory course. So it's a simplified, the sections on statistical methods are greatly simplified, but they're quite adequate to a laboratory course. And finally, a laboratory discussion by the instructor, and this is purely traditional. Typically half an hour or so of lecturing at the whiteboard using the projector and the computers. By the way, all of the laboratory computers they had Mathematica installed on them, so that students can use the software during the laboratory period. The main computer laboratory that students use at UHG is around the corner from our laboratory room, which is rather convenient. They've got nearly 200 desktop computers there that students can use, and IT people and made sure that Mathematica was installed and registered on every one of those, which I was very appreciative of. So there was a considerable change in the written materials. Let me talk a bit about the results we've obtained. And I'll sort of go through these in terms of our goals, and then report. We've only been doing this for 6 weeks now, so it's anything I say in terms of results or conclusions is very preliminary. But I think we can say something about these, how these goals are, or what's happening with the students and what we see in lab reports that we can talk about. Emphasis on symbolic solutions to problems. Wait a minute. Oh, no. Okay. When students are first introduced to a computer algebra system software like that, their first impression of it is that it's some sort of supercalculator. And indeed it is. I do find, exclamations of amazement that something that with a handheld calculator or by hand, the student would spend some time and some agony over just evaluating an expression, knowing numerical values for all of the quantities involved, that the software can do that instantly. And whereas, again, the student's experience with trying to deal with homework problems in their textbook, in the lecture course, the favorite technique is to try to pick out the odd number problems and try to match the numerical answer in the back of the book. Okay. Of course, if they found the correct solution, they'll match that numerical answer most of the time. There are some typos or mistakes, actually, in the solutions of the textbooks. But nonetheless, it's a difficult thing because arithmetic errors are easy to make and hard to find once you think. They are very happy with the fact that they can take a complicated expression involving 3 or 4 quantities that have been measured in the laboratory, plug those in, and immediately get an answer back that's correct, that's guaranteed to be correct. And there's more of that that number crunching kind of stuff to do with the added emphasis on experimental uncertainties that we used. However, what I was hoping that students would recognize, and which they are recognizing, I don't have to prompt them greatly to have this happen. Sometimes it's under their own initiative, that they realize that they're getting these very fast and accurate results, but there was a step in between. It wasn't. They're not plugging in. They're not typing in, keying in the numbers, but once. They enter their data once. Okay. And the rest of the time, the software is addressing expressions involving those input values, which are necessarily defined by symbols that are used in the software. So it is thinking through that the software can get them past the agony and tedium of doing a lot of arithmetic, what looks like a lot of arithmetic to them, and which it's very difficult for them to reach the end of correctly. The software will do that immediately. But a necessary step in that was the intermediate introduction of the symbols. It was as necessary for the software to working its wonders to have the symbols as it is for the students. So we are, anecdotally, I can say that we are having some success in conveying the concept that step of defining symbols is really a necessary one if they're going to treat non-trivial problems. Again, the anecdotal evidence that I see just from talking to students during the laboratory and talking with them outside the laboratory about writing the reports, that's having a positive effect. Let's see, I've sort of compared it to, it seems to me that as a learning experience, it's being more effective than, say, even their careful attention to the instructor deriving the result. It takes several steps and get to the end. And that, of course, is a more direct expression of the power of the CAS software and purely symbolic calculations. We include a few examples of those in the lab manual, but I really don't think the lab manual is, or the laboratory is where we're going to make a lot of difference with teaching the students to strive for symbolic solutions to problems. But they do see the value of the symbols in terms of calculating numerical results. So that is something valuable. Avoiding the calculation errors. Here I go into a specific example where this is a solution for, it's almost general, not quite, for a free fall trajectory, finding the range of an object released into free fall with experimentally determined values of the release velocity, the angle of release, which for this statement of the solution is positive. That's where plus sign comes from. And the height of the release. So this is the solution that one finds just from applying the kinematic equations and constant acceleration to the conditions of that kind of release. It looks a little hairier with when you calculate, put in the uncertainty, the calculated uncertainty, and I really haven't shown this particular one was a case where we simply told them to use a brute force method, calculate maximum and minimum values, and use their differences from the best value to determine the uncertainty. So that amounts to an intelligent calculation of that expression 3 times. I mentioned before that I've taught this level of physics to engineering students for many years in calculus-based courses. And even in those courses, I found students had great difficulty in a reasonable amount of time correctly calculating. Here, once they've, I'm showing an example of the code that was actually used given the release velocity, the angle, height, etc., where Mathematica is generating the calculation for them. Since I don't have those symbols defined here, I can't show you that calculation, but a little later I'll actually do one of the calculations. I'm not going to spend our time here. Gaining familiarity with the CAS software. This and in the next, we're basically relying on the student's initiative. And it's purely optional. We're not making it mandatory. Have any plans at this point to make the software mandatory? We do encourage their use and learning something about how such software works. And we are seeing a small fraction of the students become actively interested in learning more about the software on their own. Show some small amount of evidence for that. Survey responses down here. My most ambitious goal, and one I really didn't expect this particular project to get very far with, is gaining understanding of how a computer algebra system will generate symbolic solutions and how one can make use of that. Again, the example is the same one that I addressed a moment ago. This is the kind of code that we're presenting the students for how that can be addressed within the software. First, we start with the basic kinematic equation, apply it to the experiment and show that one gets this form, and then take that vector equation. This little statement here is just telling Mathematica to forget whatever previous definitions it might have had for those symbols so that they're clean. And then tell the software to solve that equation. And here you can see the manner in which the equation written in traditional mathematical notation is translated into a code statement using Mathematica solve command. This is telling Mathematica, here's the equation, I want you to solve it for the symbol R and eliminate the symbol TF. And then the second statement down here, the percent sign, by the way, refers to the last thing that the software had calculated, which in this case will be the solution generated by this second line. If one executes this line, and I'm going to have to walk over here to actually do that. That's a silly question that actually I can take advantage of. It's a feature of Mathematica, but it's a little beyond what we need at this point. It's the first time you tell Mathematica to do anything, it'll bring up that stupid little dialog box, and you just say no, either one. This is the raw solution generated by the software for the problem, which we are to have students compared to this, which is simplified in the manner that human beings like to read math. Of course, the software doesn't care about that, and simplifying expressions turns out to be quite a difficult task for software. One step in the simplification, the conversion of these sine theta, cosine theta multiples into sine 2 theta is accomplished with this additional command trig reduce. So that one step in going from this raw solution to the one we write in traditional mathematical notation is shown for the student. But it's actually quite a task to insist that Mathematica to give me back just the way that I want, that humans like to see it simple. But the students can see that these things are closely related to that. But we have code like this in the lab manual, and they're used to illustrate independently derivations that are done in a more traditional way in the text of the lab. And it's basically an example or showing a display to the students that the machine can handle this if you're willing to translate the equations into the input forms that are necessary. That is not generating a lot of response from students. Say something. Clearly not gaining much traction in this regard. The examples that appear in the lab manual and are posted on the lecture website for solving some problems are largely not understood by the students, and they're not being studied. And there's a couple of good reasons for that from the student's point of view. The homework problems are not graded. They tend to not pay attention to things that are evaluated. And during their tests in the lecture class, they don't have access to the software. The tests are still given in traditional. So I think some changes would have to occur in the lecture class to actually get many of the students, a significant fraction of them, actually attempting to use software like this to generate solutions to problems rather than just numerically evaluating solutions. What have we seen in the student lab reports? well, there's lots of changes, many of which are due to the fact that we've changed the structure of the laboratory, reducing the number, going through a first draft, second draft, 2 evaluations in each experiment. By the way we're doing that is their first draft is due some 3 days after the laboratory meeting, and is returned to them marked up the next laboratory meeting, and have another 3 days for their final draft. But the 2 drafts are not equally weighted. Final score they get for a laboratory experiment is 70% of that comes from the first draft, only 30% from the second draft. And that was words of wisdom from the chair, who's had experience with this form of having the students report their labs. Because if you don't weight it heavily toward the front end, they simply put it off, and you get stuff worse than what you'd get from the first draft and the final draft. So it turned out that I agree that that's probably very important to front-end loaded grading. Trying to limit this discussion, I'm already using too much time, way too much time. We see the number of errors in calculation has been reduced. They're definitely getting better numerical values out. That alone is of some value, because if they're grinding away at making arithmetic mistakes, they can't see that there's any agreement between their experimental values and the theoretical hypotheses they're to be testing. Here, but we've basically removed the tedium of generating that, and made their results from their data actually clear to them, so that they can think about, I got a value for the acceleration of gravity in their lab of 8.5 plus or minus 0.03 meters per second squared. Does that agree with the standard value, or doesn't it? Okay. And then they can decide that question. It's not a matter of, well, it was pretty close and our experimental uncertainties were small. You still get that sometimes in the versions, but not too much. They're still, at least the students are getting good results for the values, not only of the best values for the quantities, but also the uncertainties. We still have to deal with conceptual misunderstandings of the meaning of the uncertainties, and sometimes the meaning of testing a hypothesis. Many students tend to think that you've succeeded with an experiment if you pick out, among all the data you took, pick out the ones that match what the professor wants to see, the right answer, which is, of course, just the opposite of the scientific. Students are using the graphics that are produced with the software and appear in the lab manual files, and some of them are experimenting with modifying those. Not always within Mathematica, but they'll export them. Found out that the students are really computer savvy in some ways that perhaps we didn't expect. They were able to export files that I didn't know how to from we use Data Studio software as well, and they had no trouble exporting graphs from Data Studio, incorporating them into Word files. About 10% of the students in my sections at this point are actually submitting their reports in Mathematica files, where they're taking, as much as they've learned to use the software, they're taking direct advantage of. Finally, I'll show you, we did a survey, 15 questions. There's actually some comment section too that I haven't tabulated. This table 1 shows 5 yes/no questions. Are you using the software in the laboratory class meetings? Almost everyone of students is doing that. This was a bit of a surprise to me. Almost as many students are using the software outside the laboratory in the computing laboratory. the computer lab that they have access to, so that they're using the software outside the laboratory meeting time. Only about 1 in 5 have actually downloaded the software and use it, or have looked into the tutorials, try to expand their own understanding using the software. Then on some ranking questions, and 10 of those where agree strongly was choice 5 and disagree strongly was choice 1. They definitely find that the software is helpful in preparing their lab reports and in the laboratory course generally, that is handling their data. Other things that were more positive, they find the software to be general and are helpful in understanding the mathematics. They prefer using it to a calculator or to Excel. Very few, though, are using it to do anything but numerical calculations. Okay, so they're not typically using the software to do algebra, to plot graphs. Right? Most of them disagree that they use it that way. The tutorials aren't helpful to most of them. Most of them haven't used the tutorials at all. The other significant positive response, I think, is that they're expressing a desire for instruction outside the boundaries of laboratory class. They'll learn more about the software.
Can I ask you what your...
There were 27 respondents there. I've got about 52...
This is after 6 weeks?
Yeah. They had basically 3 days and a weekend, the deadline. So. Okay. I don't think we can... no conclusions we can make at this point are very solid. And even our goals are likely to change as our experience doing this increases, and we collect more data on how effective we're being with students. I think there's enough positives to say that this is the implementation of some sort of computer algebra system software in physics laboratories is a good idea. It has become, if not commonplace, at least common. There are a lot of the physics courses and math courses and chemistry courses in the larger research institutions, and particularly in engineering, the teaching of engineering and science students would involve just the calculus-based courses and upper level courses, where this software and other computer algebra system software are becoming pretty common. The large research universities in the U.S. almost invariably have side licenses. I was very surprised and happy to find that at UHD I would be able to ensure student access to this software. Could start to try out some thought that the software could be of benefit. Okay, I'm done.
Okay.
Any questions?
All right. Questions?
Yes.
Any idea what your sample population, your experiences with mathematics? I came in late, so I'm sorry if you've covered that.
If it's higher than 0, I'd be very surprised. So far, I've never heard any of the students remark that they had seen the software prior to laboratory course.
When I taught a algebra-based physics class at Penn State, one problem I ran into was the students were incredibly math-phobic in that class. And I was wondering, does using this software, does it make them more relaxed, or I mean, how did they react to it initially? I mean, I could see them either being...
There's not a uniform response in that regard. You're right. A large proportion of these students are math phobic to begin with. And many of them, upon seeing that the course necessarily is pretty serious about the mathematics, will drop out. So in all the science courses at UHD, we typically see a drop in the first 5 to 6 weeks of the census in those courses by about 50%. It's substantial. But the reaction that the math-phobic students have to this piece of software ranges from very positive when they see that, hey, it's producing the numbers and I don't have to grind them out, to more math, and they're more phobic. So I don't think there's any consistent response just because they're math phobic. There's some that have fairly decent or good mathematics intuition who their response isn't consistent either. Some of them are very enthusiastic about the software and others couldn't care less.
Can you enter in equations in any kind of convoluted order? I mean, like any number of brackets and it'll solve it automatically? Or do you have to simplify it down to a certain level?
No, the software doesn't care how complex the statements are. In fact, the basic idea is that you submit something you want solved with the solve command, say. There's lots of commands. I mean, there's over 2,000 commands in the software. It's huge. If it's a nested series of things or a list of nested series, it starts at the bottom of each nest and starts grinding away, and it keeps grinding until there's nothing else to do. And then if there's another term, it starts at the bottom of that and grinds up until there's nothing left to do. And it doesn't stop until there's nothing left to do. So as long as it's got definitions for symbols and counters to symbols, it just keeps keeping on. So there's no well, I guess your expressions always have to be finite because we don't live long enough to write infinite expressions, but that's the only limit in that regard. Of course, the computation may not stop. You can give it uncomputable expressions and it will spend until you turn the machine on, grinding away on it.
You have to be careful about anything that's somewhat iterative, calculative value later on in the calculation.
Oh, you mean like a non-linear equation or like a continued fraction or something like that?
Well, just an implicit or next loop.
Oh, yeah.
It's very easy to get into that where you define something, you find it a little bit later and reuse it, and you'll make a small error.
Right.
And
that's
the error is up
way
at
of
the top.
generating nonsense. Yeah.
Can I ask you actually to move back up in your presentation? Is that possible? Right there.
Uh-huh.
So I'm a little confused by that R arrow. You're introducing, if I may, you're introducing not only for the math challenge students, not only a lot of extra math sometimes, but now an additional syntax that they have to learn. Sometimes it's not so bad. The first, in one, that's not. You can tell them that everything's going back to undefined. That's not too bad. All of a sudden, they've got an R arrow and out 2, right?
Right.
And Mathematica uses that because it's very general and it tries to give you the most general solution. So I can imagine them coming across a quadratic equation. And all of a sudden they have some complex solutions. And the output in Mathematica sometimes for solutions that require complex mathematics, they can go on for almost a page.
Sure.
So is that more or less, or do you avoid that in Physics 101?
This is as nasty as it gets in this Physics 1 course.
So you control the complexity?
Well, yeah, but it's the whole curriculum controls the complexity of problems that those students will see.
And in addition, your approach here in the Mathematica format is to make sure they never run into that.
Yeah, if that were a danger in any of these lab experiments or in a homework problem.
Well, like for Physics 2, right? No. Or, something follow on, a little bit more complex, future expansions of what you're doing here.
In electrostatics, for example,
Yes.
this finding exact solutions, and then you can also use limit processes to find approximate solutions. A frequent occurrence in the calculus-based physics 2 course is you're calculating, say, the electric field of, a charged plate, for example. It's the small difference between two large quantities in the neighborhood. You can push this to the point where you can also develop how you find an approximate form for that solution that numerically can be more stable than the exact form, because it does not take the form of the small difference of two large quantities. But that's pushing the physics 2 students a bit, I think, in a calculus-based course. So, yeah, I guess I'm thankful that there's no temptation with such problems, because this is about as difficult a math problem as they face in the entire course. The algebraic-based, and this does involve the quadratic solution as well. Yeah.
My name is Alex Monchek. I'm taking the course as a continuing education student at this course here. And I was wondering if you could talk a little bit about how somebody would first start to get involved in Mathematica. Because the project I'm doing for this class has to do with evaluating the presentations and correlating the presentation aids that the instructors present with the understanding that occurs. And I'm using, I noticed in your surveys you used a yes-no answer and a strongly agree, disagree. In the engineering management classes we took, there was no scale that we could find in existence anywhere that bases on a golden mean, because physics and engineering is all about balance between things, and there was no scale that was like a 9-point scale with 5 as the golden mean. So we developed our own scale in engineering management where we evaluate the balance on things. Have you run across a scale like that, and how would you start?
I haven't run across that. In fact, just composing this survey, which I did myself, and it made me think, even as I was writing it, that I really don't know how to design this questionnaire to get the information I'd like to get out of it. And an idea like that might be valuable. But so no, I just sat down and said, these are 15 questions I'd like to ask the students and see what they have to say about it. So I was very naive and not something I'm an expert at.
People have the feedback or pullback about having an advantage?
No, there hasn't, no student complaints about that, and I'm not aware that any of the students coming into the class had ever seen the product before, or any other CAS software like Maple.
CAS is being used in other departments or
Oh, he was asking about biology.
MathCAD or MATLAB, products like that.
Double E, I'm sure they're using.
Again, I would be surprised, and I haven't heard any talk among the students or from students to me that indicate that any of them have any such products
Well,
at all.
part of it here is that they may have taken this course before they take any other course that's going to use it.
Yeah, most likely. Yeah. Well, hopefully, actually.
How does this software package compare to the other ones that are used for the same thing? Like you mentioned, MathCAD and Maple.
If I answer that, I'll sound like a salesperson so I think I'll just decline to answer that. Except to say that I think it's much more powerful, much more fun.
MATLAB is pretty ubiquitous in the double E department.
Yeah, I know.
Especially in control theory. Dave's using this to a variety of different software here.
Yeah, I used Maple quite a bit when I was in graduate school and a little bit in undergrad. And I've used, Mathematica, it's easy to get a copy of it here because I think we have a site license.
Well, I love
And-
what you do.
Yeah. And I taught a course for graduate students on using Mathematica to solve physics problems. The only problem was that the name got shortened to using math to solve physics problems, and a few people showed up who...
I was there.
Yeah. A few people showed up and they didn't quite make it all the way through, but it was because it was some really sophisticated problems. They were,
Yeah, yeah.
I mean, a lot of.
Right. Yeah, one of the advantages is that you can point students to nonlinear differential equations. Well, that's even a little bit of a push even for Mathematica. But numerics are also very strong. So nonlinear problems often can be solved numerically with
Yeah.
this product.
And there's even tensor packages for these for solving
Yeah.
like relativity problems.
And using it in junior level computational physics courses has been, become very popular in places like Illinois.
Well, of
Yes.
course, Illinois.
You might want to tell them about the notebooks.
The-
Mathematica makes available the notebooks.
Speaking of the demonstrations, or the Mathematica files are called notebooks.
Right, but I mean, there are so many through certain people that have an expertise in an
Yeah,
area.
there's third-party add-ons to, and there's hundreds of those. Almost any specialty that you might go. You can go to Wolfram's website and go through the list of packages. It's a super number. I found the demonstrations. I've downloaded for my lecture class at this point about 18 or 20 of those demonstrations that they were mostly written for high school physics, but they suited this course very well.
I'm sorry, so you use this in your lectures?
No, I'm not. I do present class notes, and I write almost everything down there. So those are written in Mathematica, and the students that do get the software can download those. They can play with the solutions that I present there. Or they can just download the Acrobat file and read them, and that's all they can do. But now what I'm speaking of with the demonstrations are the feature of Mathematica that came out with version 6, where it becomes relatively quite a simple task to produce simulations.
Animations.
Animations,
Yeah.
2D or 3D. And people have written a lot of those for physics. Well, their demonstration site has almost 3,000 demonstrations now, ranging from piling and art subjects to mathematics and physics and chemistry. And I've picked out, like I say, a little less than 20 at this point. I thought were especially appropriate to algebra-based physics class. And some of the students have noodled around with those. That's basically outside the class adjunct to the lectures. That's some of the things, a more interactive way. Students can't get the maximum benefit of those unless they have the full software.
That's one more
Yeah.
question. Having been a physics lab TA life, require your TAs to know Mathematica up front so they can...
I don't have any TAs, so I don't.
That answers that question. Okay. None at all, really.
There's myself, and I've been using Mathematica for about a dozen years now. And Dr. Grebowitz
So
and
you
Dr.
teach all
Goldberg.
your own labs? You teach all, you teach
Yeah,
it?
yeah.
Wow.
This actually goes on, yeah.
Okay.
And no, we don't have any lab assistants, and neither of the other instructors, they're both PhDs, had ever used Mathematica before. So they're learning as they go along it as well. But there's we're not really insisting on the students learning much about, writing how to solve problems. They're not writing this stuff from scratch. They're basically saying, here's how you can do the calculation. Having them edit those in some cases so that it applies to their particular lab experience, but I'm not having them sit down. Mathematica does, it's famous and notorious for having a steep learning curve, which is true if you want to learn general applications of programs. But simple things like this, introduced as examples, I think they can learn quite a lot about the software, on-the-job training kind of thing.
Also, I think the students, they tend to be a lot faster to adapt to technology, too.
Yeah, they're willing to try it, find out if they like it or not.
Any other questions? Okay.
I'd like to thank you for your attentiveness, for bearing with me while I went over time, I'm sure.
Well, thank you.